Hello. Today we're going to start a new topic, graphical models. So graphical models were one of, if not the dominant approach to machine learning prior to the deep revolution. And they have survived the transition and are currently integrated with deep methods in a couple areas. So in speech recognition, there's something called connectionist temporal classification, which is a form of deep graphical model that we'll get to in a few units. In the state-of-the-art, parsers are also, in a way, deep graphical models. They still use the CKY dynamic programming algorithm, which is closely related to graphical models. So what is a graphical model, and how does it differ from other models like language models? So now we're interested in the structured case. We're interested in the structured label. So in language, say in machine translation, you have an input sentence and its translation. And both the input sentence and the translation are structured objects. They have many parts and many words, and for each word, there's a large choice of possible words. But the typical language models are autoregressive, meaning that you're predicting one word at a time, and you're taking a softmax over the possible words at each point in time. So in that setting, it's easy to compute the probability of a given string, and it's also easy to sample from that probability distribution. We're going to talk now about sort of a general setting where the models are not autoregressive, and where these problems of computing the probability or sampling from the distribution tend to be intractable. So in the general case, in the special cases of CTC and CKY for parsing, you get a tractable version of a graphical model. But in the general case, they're intractable. So here's an intractable case, semantic segmentation. So in semantic segmentation, you're given an image, and you want to classify each pixel in that image as to what semantic category does the object at that pixel fall into. So we want to assign each pixel one of some number of semantic classes, for example, person, car, building, sky, or maybe other, a catch-all. And what you can do, or what was often done, is to construct a graph on the pixels where each pixel is connected to its four neighbors in the graph. And so what we're going to consider now is probability models over assignments of labels to the nodes of a graph. And this is going to be easier to talk about if we're more abstract than talk about a completely general graph. I love abstraction. So consider a completely general graph. And what we're interested in doing is assigning a semantic label to each node, like a semantic category, person, car, or whatever in the case of vision. So we're going to have, so by y hat, I'm going to mean an assignment of a label to every node. And this y hat is a variable that's going to range over all possible assignments. So given y hat, I'm going to write y hat of n for the label that this y hat assigns to node n. So y hat is assigning a label to every node. Y hat, you can think of that as a kind of field on this graph. Now we're going to assign a score, like an energy score, to each y hat. And we're going to assign that score by assigning a score at each node for that node having the label that this assigns to it. And we're also going to assign a score for each edge in the graph that says how compatible is the label here with the label here. So we've got these, we call them unary scores, unary potentials, people will often say, and binary scores or binary potentials. And the score of the complete assignment is the sum over the nodes of the score of that label assigned to that node. So I'm going to assume a tensor here. This is a tensor that takes a node and a label and returns a score. And we can actually store this in a tensor because it's just the size of this tensor is the number of nodes times the number of labels. And so but the score of the whole labeling is also going to include a sum over all the edges in the graph of a score for that edge. So that score for that edge can be stored in a tensor. That is, the first index is going to be some index for the edge. And that edge is going to have two endpoints and an M, and then this score is going to look at the pair of labels assigned across that edge. And for each edge and each pair of labels, it assigns it a score. And that gives us a score for the whole labeling. And when you make this compatible with deep learning, what we want is that these tensors that are used, that are small objects, right? This is the number of nodes times the number of labels. We want these tensors to be computed by a deep neural network. So we're going to assume that there's a deep neural network. Say we're doing semantic segmentation for images, then X would be an image. So we're going to take an image in, and given that image in, we're going to have a function, a deep network, that for each node and each label computes a score for that label at that node. And the same thing is going to happen for the edge tensor, right? We're going to take the image in, and for each edge in our graph and each pair of labels, we're going to get a score for that edge and that pair of labels. And then that's going to give us a score for this whole labeling, the labeling of all the nodes. And we want to take a softmax over all labelings of the score of the labeling. So we're defining a probability distribution on the global labeling by taking a softmax over all possible labelings of this score that's looking at these tensors. And then our loss will assume that we have labeled training data. So we have an image together with its semantic segmentation. Somebody did it by hand. And given that, if we have a gold semantic segmentation, a gold labeling of every node, our loss function is just the cross entropy loss. This is the classical loss function, our fundamental equation of deep learning. But now we're talking about a probability distribution over all possible labelings. For a general graph, this problem is easily proved to be intractable. This probability is defined by an exponential softmax over the scores, and it's easy to prove that computing the normalization constant of that softmax. Remember, the probability under softmax is 1 over z times e to the score. And that z, that normalization constant, computing that is sharp p hard. You have to count there's an easy reduction from Boolean satisfiability, where z is just the number of satisfying assignments. And that's the primordial hard counting problem, counting the number of satisfying assignments to a SAT problem. So we've got this, we're assuming a deep network that's computing these tensors. And these tensors are manageably sized. You can iterate over the entries in this tensor. There's just, this is just the number of edges, and we'll assume the number of edges, it's a sparse graph. So this is typically on the same order as the number of nodes. So this tensor has number of nodes times the number of labels entries. This has the number of edges times the number of labels squared entries. So we can assume that these tensors can be stored. It's a compact representation of the function on the labelings. So now, if we've got these tensors and we've got a gold label, we can actually compute this. What we'd like to do is to compute this cross entropy loss. And in particular, we would like to be able to take this loss, which we can't even compute because we can't really compute this probability because we can't compute z. But nonetheless, we would like to get a back propagation of this loss back propagated into these tensors. If I could get the gradient of this tensor with respect to this loss, then I could back propagate that back through the neural network that produced this tensor. So what's the thing that is making this challenging or really difficult is just back propagating this loss, which we can't even really compute, back into these tensors, right? So there's an exponential softmax back propagation step. The back propagation step across the exponential softmax is now problematic because we can't even compute z. And that's going to be the topic of the next unit. Thanks.